Hello everyone and welcome back to lecture 7. In this part of the lecture we will look at fouling and how the factors of fouling affect the overall heat transfer coefficient. Okay. Um, so in the previous part we talked about that we can calculate the heat transfer coefficient by looking at the overall resistance of the system, and we looked at a tube where inside the tube we have a hot fluid and outside we have a cold fluid, for example, and then we write that we have three basic resistances in this system. So we have the convective flow inside the tube, we have the conductive flow, that is conductive resistance, that is in the wall of the tube, and then we have the convective resistance outside the tube as well. Okay, and then we said that we are using here the mean area because we are in a cylindrical system, and as such we want to know what is the effective area for heat transfer. So now let's look at the effect of fouling. So fouling, as we know in our common life as well, that it's one, for example, when we have some form of scaling on our heat transfer tube, and this could be because of the salts present in the liquid. So precipitation or crystallization of different salts can cause scaling, and that's one form of fouling. But we can have also other situations, for example, when we have polymerization or the reaction of the components of the liquid inside the tube with the wall of the tube. Okay, so because of this reaction, we can have this form of fouling around the inner tube, but we can also have fouling outside the tube due to the fluid in the shell as well. Okay, so if you look at this situation here, for example, so you have the convective resistance of the fluid that is inside the tube, and then this fouling layer adds up an extra resistance that is due to the fouling layer, and then we have again the tube resistance and then the conductive resistance. So this fouling layer kind of impart new resistance to the heat transfer. Similarly, we can have other situations where we can have, for example, if you have oil inside your system, and the oil can cause oxidation, so we can have a tar formation, for example, and that can significantly reduce the heat transfer as well. Then we can have some other systems like biological fouling. If your system, for example, if we are using a biological feed, the slimy bacteria or viruses can stick to the surface of your body and can build up slime, and that slime is what we call, for example, biological fouling. Then we can have another situation that is like rust formation of your tube, and this rust also in times build up with other forms of fouling and then can contribute to the additional heat transfer. So here there is a link to a video that you can have a look at what are the different types of foulings. Okay, most of the time there are different fouling mechanisms happening at the same time, so you can have scaling and you can have rust formation and other contributions to fouling as well. So fouling factors are actually introduced to account for the fouling, because fouling is quite complicated, because if you have fouling in your system, we are not sure what is the thickness of that fouling layer, and we are also not sure what is the thermal conductivity, because we are not sure that what is the mechanism of that fouling layer. It can be, as I said, it can be one mechanism, but at the same time it can be multiple mechanisms all acting at the same time, like biological fouling, rusting, scaling, all can happen at the same time. So one easy way to look at this, for example, fouling, is to use fouling factors. Okay, so people have developed these fouling factors over the year for different systems, and these fouling factors obviously depend on a range of systems, like what kind of feed you have, what kind of flows you have, what kind of temperature and pressure conditions you have. So these are all accounted for in these fouling factors. And these fouling factors have unit of meter Kelvin per watt. And if you notice this unit, that it is actually the reciprocal of heat transfer coefficient. Okay, so fouling necessarily is 1 over u, so it means that it's the opposite of heat transfer coefficient. If we look at the formulation of heat transfer coefficient now and look at fouling, so we can write R, that is the total resistance of the system, okay? And so we can write it here. For example, we have the convective flow, the convective resistance due to the fluid inside the pipe. Then we have the fouling resistance due to the fouling inside the pipe tube layer. Then we have the conduction resistance due to the wall of the tube, and then we have the fouling resistance at the outside of the tube, okay, towards the shell of the heat exchanger. And then we have the final convective heat resistance that is due to the shell fluid. Okay, so the reason we write F over A as our resistance, because we know that R is equal to 1 over UA. Okay, and we defined F as 1 over U in our previous slide. So if you use these two equations, you can write F is equal to R is equal to F over A. So based on that, we have used F over A. Okay. Now, one important point is here that U is always associated or is calculated based on the area of heat transfer. So in this equation, we are not sure what is the area of heat transfer. And from you can say calculation and also from experience that people have learned to use the outer tube area as the basis for calculation of overall heat transfer coefficient. And the reason we use that is because the main mechanism of heat transfer is happening at the outer surface of the tube. Okay, so that is why we always use outer surface of the tube as a basis to calculate U. Okay, so if we use this information, we can expand our equation. So we can expand this simple looking equation, although it's not simple, but it's relatively simple compared to the next one. If you expand the different areas into diameters, we can write this equation here. Okay, so it's much longer equation. Now let's have a look at how we can actually derive this equation, starting with this equation. So how we come to this equation here. Let's start with our main equation. So here now we are defining our R, that is the total heat transfer resistance to our system. We are defining it based on the outer surface area, that is A node or AO, that is outer surface area. And if we do that, we can write this equation in this form. Okay, so instead of 1 over UA, we are writing 1 over UA node. And if you now just rearrange this equation, so we have 1 over UA on this side, and then we take 1 over U on this side, and then we take the outer surface area of the tube and multiplied it on the right hand side. And then in the next lower equation, we have taken the reciprocal of 1 over U, so that is U. And on this side, then we have 1 over this term multiplied by A node. Okay. So we can further expand this equation here by defining, for example, the areas in the form of diameters. Okay, so we can write a general expression for area, that is pi d. Okay, and here we are defining the surface area of the tube pi d, and that is based on per unit length of the tube. Okay, so it means that the length of the tube in this equation, we are assuming it's 1 because surface area is pi d L, and L in this case we are assumed it's 1. Okay, and now if you use this definition of area and replace all these A terms in this equation in the form of diameter, so here we will have pi d A node, pi d AI, pi di. Similarly, same here and for others, okay, as well. So if you do that, we can write it in this form. As I said, we just expanded the area with this formulation and we got this here. Okay. So this equation looks quite simple. The only thing that we haven't expanded is this part here, because here we have a node that we can expand as pi d node, but here we have the logarithmic mean area. So let's see how we can expand this part of the equation. So if you use the definition of am from our previous slide, so we can write this equation, we can simplify it like this. So how we get to this equation? So we know that uh, sigma over lambda am times a node is equal to, so here we have put the value of am. So value of am is a node minus ai over ln of a node over ai. Okay, and again we use the same definition of surface area as a is equal to pi d, and if you expand all these area terms, you have this equation in the form of diameter instead of the areas. Okay, and then we also notice that d node minus di, the the difference between the outer diameter and the inner diameter is actually the thickness of your tube. Okay, so d node minus di is sigma here, so sigma will cancel out with the sigma on in the denominator, and then we have the final part of the equation as d over 2 lambda ln d node over di. Okay, and that is what we replace here, as you can see. So we expanded this equation, this part of the equation, by using this simple analysis, and we get this final equation, very long equation. Okay, so don't worry that you don't have to memorize this equation. This equation would be available to you if we have any question related to this equation. This is our final equation that is based on the outer surface area of the tube as the heat transfer area. And let's see if we can actually simplify. Okay. So first, let's look at that. What are the different terms involved in this long equation? So although it looks quite long, but all the terms are quite simple to understand. So here we have HI, that is the tube side convective heat transfer coefficient, because that shows us that this part of the equation is due to the convective heat transfer resistance. Then we have Fi, okay, so that is due to the tube side fouling factor, and that is due to the resistance due to the fouling factor. Okay, then we have the thermal conductivity of the wall of the tube, and that comes because of the conductive resistance to the system. And we have shell side fouling resistance, where we have the fouling at the outer side of the tube. Okay, and finally we have the contribution from the shell side convective heat coefficient, and 1 over h node mean that this resistance is coming from the convective heat transfer outside the shell. In addition to that, we have d node, that is the tube side diameter, okay, outer diameter of the tube, and then we have di, that is the inside diameter of the tube. Okay, so to solve this equation, you need to know 1, 2, 3, 4, 5, 6, 7 set of information to solve for overall heat transfer coefficient. Now, this is the equation when we are considering all the resistance in our system, but we can be sometimes in situations we can actually simplify this equation further to make it more manageable for calculation. So one simplification that we can do, depending on if you have this option available. So let's say you have a heat exchanger where the tubes of your heat exchanger are very thin. Okay, so it means that you have very small thickness of your tube, and it as such the surface diameter, the inner and outer diameter of your tube are very similar. Okay, and this can only happen if you have very thin heat transfer tubes. Let's see if we use this approximation, how we can simplify this long equation. So if di is equal to d node, it means that the ratio of these two diameters will be 1. Okay, and so if you do the simplification, so here is 1, now here it will be also 1. In this case it will become all 0. The reason being that it will be log of 1 and log of 1 is 0. So this whole contribution due to thermal resistance of conduction will become 0. And this is the same case as we discussed in the previous part as well, that when we were defining heat transfer coefficient without fouling, that when we consider thin wall tubes, we can ignore the effect of conductive resistance. So we can simplify this equation, and we only get this much, you can say, short form of equation, where we have the U, that is the overall heat transfer coefficient, equal to convective heat transfer, the fouling resistance due to the inner side of the tube fouling, and then we have the fouling resistance due to the fouling at the outside of the tube, and then we have finally the convective heat transfer at the outside of the tube. So we actually got or removed, we removed the thermal resistance due to conduction from this equation. Okay, so this is our final equation for overall heat transfer coefficient when we are considering fouling at the inside and outside of the tube. Okay, and this equation is applicable when we have thin walled tubes. So if you don't have thin walled tubes, then you have to go back to this long equation here, and you have to use this equation because we cannot simplify it further. We have to use different diameter values to simplify for U. So in case if you have thin wall tube, you can use much simple equation. And so here, as I said, this fouling factor is due to the inner side of the tube, and this fouling factor is due to the outer side of the tube. Let's say you are in a system where you have only fouling inside of the tube. So it means in that case, you can ignore this F node and you will just consider Fi. Okay, so you have to adopt this equation to your system. So that is for the case of fouling. Now, just to remind you how the equation was when there was no fouling. So when there is no fouling, we can make these fouling factors as 0. Okay, and then we can calculate U for a thin wall system just by looking at the convective heat transfer resistances. And this U is what you will see in the next lecture as well, or in the design of heat exchanger design. This form of U is called clean heat transfer coefficient, clean overall heat transfer coefficient, while this form of heat transfer coefficient is called actual heat transfer, overall heat transfer coefficient, because here we are considering all the fouling effects as well. Okay, so these are the two important equations from this part. One is when we are using U as a clean system without considering the effect of fouling, and then the next one is that how the fouling affect the value of U. So we have to account for these fouling factors. That is all for this part. Thank you so much for your time.